This video is going to be about how electric charges affect each other. If you throw a bunch of electric charges into space, they interact. They put forces on each other, and if you try to move them around relative to each other, you have to do work. Like if I was going to force these two positives together, that's going to require work, and that's going to change how much potential energy is stored. Everything we learned about gravitational potential energy and gravitational force is going to help us here. But things are more complicated because electrostatics are both attractive and repulsive, and we can also throw lots of charged objects into a relatively small space, and we have to consider the net effect of all the forces on each other, all the particles on each other. So just to kind of give an idea of how tough that can be, let's take a look at how these two big charges affect these two little test charges. A test charge is an important concept for mapping the field around a charge we really care about. So just like the Earth alters the space around it and creates a gravitational field, and that affects things like me and you in a textbook, we don't really think about the textbook's gravitational field. It's so small compared to the Earth that it doesn't really matter. That's what we've got going on here. These charges are supposed to be wicked big. These charges are tiny. So we're going to see how these alter this space and how that affects these if we happen to put them in. Well, for a positive test charge, we could see that there's going to be a repulsion. I'm trying to draw this so it's along a line between the center of the two charges. We're also going to have repulsion between these two. It's going to be a little bit less because it's farther away. So the net force on this particle due to these other ones is going to be the sum of these two force vectors. I'm going to add them using the parallelogram method. And we end up with a net force kind of in this direction. Of course, as the particle accelerates along this, it's going to change its location, and the direction of net force is going to be changing. So it gets pretty complicated. I'll throw in the forces for the negative charge now. So we can see that the negative force is attracted to the positive charges, giving this net force in this location. It's really hard to keep track of these, and they're changing continually. So it would be useful if instead of trying to add forces individually for the charge wherever it ends up being, if we could just map space and come up ahead of time. In this location, what do we know about force? In this location, what do we know about force? In general, we have a concept called field, which is related to force. In every force equation, which I've drawn in purple here, part of it depends on where you are, and part of it depends on the specific object. And field is the part, either gravitational or electric, that depends on where you are. The same is true with something called potential and potential energy. I've drawn basically the equations for potential energy, and everything to do with location is in red, and everything to do with the object is in green. So potential is the location-specific part of potential energy. So we've seen that the electric field is a way of visualizing the force that a charge would experience if it's brought near another charge. We basically put a small, what they call a test charge, nearby our original charge. And we ask ourselves, what direction would the force be on that charge in that location? It's not hard to imagine that it would repel. So it'd be something like that. And basically we go around and we put the test charge in lots of places. There appears to be lines diverging from the big charge. That's the the force of gravity spreading out over larger and larger areas, exceeding the force of electricity. And it shows that that force is getting weaker. So the picture is helpful for us to understand that. But we do have to remember something, and that is that I put a positive test charge there. What if I had put a negative one? Well, in that case, it would be attracted. It would be doing exactly the opposite of what the positives are doing. So it would be kind of being pulled back along this line. We always draw it as if our test charge is positive. So if you threw a positive here, it would experience force along these field lines. You just kind of have to remember, if you throw a negative in there, it would experience force opposite those field lines. If I had a charge and I put it, say, here, I asked them where they would expect other charges to have the same potential energy. And they told me in a ring around the first charge, that if I put this guy anywhere here, it would have the same potential energy. Similar to that. So the equipotential lines around a positive charge, the places where some object would have the same potential energy, are spherical. So here's a better picture of what I just did. Any positive charge, like this cursor, is going to experience a force away, and it's going to be moving to lower and lower potential energies as it moves to these different potentials. If we sort of graph electric potential on a z-axis in a 3D chart, it becomes easier to see what's happening. This positive charge would be going to lower potential energy, and it would be being converted into kinetic energy as it rolled down this mountain that's electric potential is represented by. So we would expect a force downward if this was a ball. We'd expect going to lower potential energies and therefore higher kinetic energies. So we can imagine this charge kind of rolling down the mountain. Of course, we're at a negative charge. It would be being sucked up the mountain. That's kind of a hard thing to see. That's difficult about static electricity. It can be both attractive and repulsive. So how many lines did I draw? I drew 8 because I think it kind of looks nice. And it's really symmetrical. It kind of shows the pattern. But clearly I could have drawn an infinite number of them. Could have drawn one at every single location. So you pick a reasonable number. But what's important is that when you're dealing with more or less charge, the number of lines should be proportional. This charge affects space a certain amount. This one's going to affect it twice as much. So I should draw twice as many lines. So I drew 8. This time I'll draw 16. 1, 2, 3. So that's one thing to keep in mind. We can clearly see that this is affecting space more than that is. I had students look at a negative charge. Notice that the field lines point inwards because a positive would be attracted to that negative. And obviously there's also spherical potentials around it. So in 3 dimensions, it would look like this. A positive would fall to lower potential energy. It would speed up as it did that. It would gain kinetic energy. Notice I have the same number of lines on this negative that I do on this positive because they represent the same amount of charge. Last topic is how do field lines interact between different particles? Well, they have to go out of the positive into the negative. In this case, they have to go out of both positives. So, best thing to do at first is to draw the correct number of lines that you've decided on coming out of your charges. So I've got 8 on both of them. It's got to be going out of this guy. It's got to be going into this guy. And all we do at that point is we start connecting the lines. But we could figure out that if I put let's say a test charge here. Here it's going to experience a force away from the positive and towards the negative, and apparently along that line. Of course, a negative would have felt the opposite. In this case, they all got to come out all the way around. So let's start to draw these two. This one's going to go in this direction. This one's going to go in that direction. But here's the deal. The lines can't really cross each other because they represent the force that a particle is experiencing in a certain location. So as these guys approach each other, they have to kind of curve away from each other and not cross. The same thing happens here. Here's the equipotential lines in yellow and the electric field in red if you have two positive charges. Notice the electric field lines approach each other but don't cross. That's because the electric field shows you the direction of the net electrostatic force in a location, and you can't have two net forces. So right here, we would see this positive charge is being accelerated that way. Here it's being accelerated that way. We have sort of strange looking potential lines. They kind of bunch up in the middle. And what's happening there, if we plot it in 3D, is we sort of have a saddle shape. This would fall to lower potential energies, but if it stayed directly between them and continued this way, it would then go about higher potential energies. So with a saddle, it could fall off here and go behind, or it could fall off here and go up front. But basically, there's no place where the contribution to potential energy from one is completely canceled out by the other here. Because if we're going in this direction, here we're falling to lower and lower potential energies, but now we're going back to higher and higher. And the shape of the saddle really shows that. Contrary-wise, if we have a positive and a negative, in some ways, the equipotential lines look kind of similar. Notice that the field lines look pretty different. In this case, we'd always experience a force away from the positive and towards the negative. So as we look at this picture, we should notice there's a relationship between the field lines, which tell us the direction of electrostatic net force, and the equipotential lines, which tell us a little bit about the potential energy in each location. They always seem to be perpendicular to each other. And that relationship holds up, and it kind of makes sense because clearly what direction you're being pulled and how much potential energy you have are closely related. When we look at this pattern, we can't forget that my positive test charge, which this little magnifying glass represents, it's both being repelled from here and attracted to there. So it makes sense that the net force would be in this direction from both those charges. And we can see that if I move my positive charge in this direction, I'm going to be releasing potential energy and probably gaining kinetic energy. So if we visualize that in 3 dimensions, maybe it would look something like this. Here's our potential peak. Our object could roll down the peak and into the well. And there's a place in the middle where we're balanced between the effects of the positive charge and the effects of the negative charge. We're going to investigate this setup in class for real. And the way this works, we have this conductive paper, and embedded in the paper are these little spots of conductive paint which have push pins through them. If we hook those up to a power supply and put the positive of the power supply on here and the negative over here, this will give similar patterns to what we'd expect if we had a positive and negative charge. We can use a multimeter set up to measure potential in DC volts. And if we hook the negative of that meter up to our negative terminal, we can use the positive probe to move around and find what the potential is at different locations. So I'm going to have students pick a spot and find its potential. And then they're basically going to start mapping out, finding other places that have that same potential as they move around the board. So for example, I found a place where the potential was 3.88. So I'm looking for places where the voltmeter reads 3.88, and I found another one here. And I'm going to find 4 or 5 more places where it's 3.88, and I'm going to connect it with a smooth curve like that. And since those are all the same potential, these are the equipotential lines. Once we have the equipotential lines, we can make a really good guess at the electric field shape because we know that the electric field will be perpendicular to the equipotential lines. So in this way, we can find out a lot about how space is altered around a positive and negative charge. I asked one other situation. I asked people to look at a line of charge. So I had people put lots of positive charges in a line and lots of negative charges in a line. And sort of what we see in between is we see that between them, we have a really constant electric field. No matter where you are here, if I've got a positive charge, I'm always going to be repelled from the top and attracted to the bottom, and vice versa for a negative. So if we were going to do a 3D picture of that, it would actually be something like this. Positive charges would be like rolling down a ramp. Negative charges would be like rolling up a ramp. Parallel plates like this are a device called a capacitor. We'll spend a fair amount of time talking about them in class because they're not only useful for causing constant electric fields like this, but they're a way of storing energy. But the best way to understand the energy of a positive charge as you move it around inside a capacitor or a negative charge is to think about how a constant electric field like this is very much like a constant gravitational field like we would have in our classroom. We know that if the gravitational field is constant, the potential energy at any height above the ground is mgh. Whether it's a big mass or a little mass, the GH part of mgh just depends on where you are. So we could say this is one gravitational potential, another gravitational potential, another gravitational potential. And they have the equation GH to describe the potential. The potential energy of an object in that case, mgh, you just multiply the mass times the gravitational potential. So we could do that with charges as well. We would have one electric potential at the negative plate. We'd have another one in the middle, another one here. And it would be an increasing electric potential as we see here. And what's the potential energy of a charge in any case? QED, which is just the electric version of mgh. What's the potential in any place? Just ED, the GH for electricity. And we can calculate a potential energy at any location by multiplying potential by charge. So we can check this in the lab if we paint stripes on the conductive paper. And we can verify this with our voltmeter that it will read 0 at the negative plate and it will increase somewhat linearly as we move up, and it will read 6 at the top plate. I hope that helps a little bit with your understanding of potential and field.